let's say that we want to compare whether blondes or brunettes, incorrectly spelled, I think, right? Two N's. Blondes or brunettes have higher blood pressures. Okay, so let's say this first group has a population that looks something like this. This is the population distribution. Okay, with an average of say 95. Okay, and this distribution has an average of say 100. This is for the entire population. So now, if I looked at this, right, in real life, what this might look like is that this population and this other population would be really close together. Here's a mean of 90, here's a mean of 95, or 95 and 100. Okay, they'd really overlap quite a bit. It would be if I just took an individual blonde, right? It would be very hard for me to distinguish whether they would have higher blood pressure than a brunette would. But the populations themselves, on the average, may have significant differences, but they overlap quite a bit as populations. So now we know when we take samples, things happen to these distributions that make it a little bit clearer how different that they are. Now we're not just looking at one individual at a time within these two populations. Now we're looking at a representation of what the average for the entire population is. So if I took a sample size of size 10, well, now this distribution might look something like this. This is a sample distribution. It's repeated samples of size 10 would still have an average for all the samples of 95, but it would be much narrower. And repeated samples of a size 10 for 100 would similarly be narrower. So now if I compared the samples to one another, right, this might be 95 and this might be 100. So if I take a sample of of blondes, sample size 10, find the average, well, the likelihood that I would find an average of 10 blondes that had a blood pressure that was likely to be the same as brunettes now is much smaller. It's only this end of that distribution, that proportion of that distribution. This is what we're really after. We're really after separating these into groups that we can identify whether or not the means of the two populations, the two groups, the two experimental groups, whether the means are really different than each other. And we know if I went further, excuse me, if I went further and took a sample size of 100, then this would be really narrow, and this would be really narrow, and I might really be able to distinguish between these two much more easily. Okay, so sample size has a lot to do with this. The other thing has a lot to do with it, just like we were talking about ANOVA, or the not for this test, okay, is that if the differences were 90 and 120, well, that difference would be much easier to distinguish. You wouldn't need anywhere near as big a sample size to be able to tell them apart. So we're going to use our knowledge of sample distributions. We're going to use our knowledge of sample distributions to help us to prove when two populations are different from one another. Okay, that could be a population of diabetics and non-diabetics, see if there's a difference in their diet, see if there's a difference in their blood pressure, so on and so forth. Or it could be a comparison of two drug groups. In other words, one group gets a blood pressure medication and the group doesn't. Is it really reducing their blood pressure when they take this medication? And if we take a large enough sample, we'll be able to distinguish even small differences between the two groups. Okay, then we have to decide whether they're really significant to us or not. So that's really what we're kind of after here. Now, one of the issues here is whether or not, how much error that we're willing to accept. Okay, and I'm going to just go over here, and actually I want to come back here a little bit because I want to get, and before I get into that, I just want to show you this. Okay, so now let's talk about error. Okay, now if I have a group, say population A, and I say to myself, okay, here is the distributions of sample size 100. Okay, now I know that, well, the mean that I got for this particular sample was, say, 89. And the standard error that I calculated, right? Now, my standard error is my standard deviation over the square root of n. Okay, now, if you know the standard deviation for the population, you could just use that and divide by 100, square root of 100, which would be dividing it by 10. If I don't know what it is, then I have to use those 100 persons that I had in that sample, 100 numbers I had in that sample, to calculate an estimate of the standard deviation, divide by the square root of n. And I got a slightly different, a little less accurate situation, but it's still the standard error. Right? Two ways that I could calculate that. So that standard error describes how this is spread out. So I'm going to say for a moment that the standard deviation of all of these 100 numbers is equal to, let's say, is equal to 20. Okay. Now, if I look for my standard error, it's going to be equal to standard deviation divided by the square root of the sample size, which is going to be 20 divided by the square root of n, which is 10. 100 square root of n, the square root of that is 10. And that's equal to 2. My standard error is equal to 2. So now, if I now compare this, if I look at this, I'm saying to myself, well, 95% of the samples that I would get of this size, or a better way to even look at it is, I'm 95% sure that the real population mean for this is between two standard deviations above 89, really 1.96, or two standard deviations below the mean. In other words, it could be somewhere between 85 and 93. Okay, I'm 95% sure that those two, that the true population mean is between those two. Now, if I take a sample and I say to myself, okay, I take a new sample from from what may or may not be another group, I don't know, another population. Okay, and my mean for that population comes out to be 94. Well, a mean of 94 would be over here in my sample. Sample size is 100 again. I mean, I would expect that to occur only all the way out here. And I know that's 2.5% of the time I'll get from this population A, I'll get them, if I take a sample of 100, 2.5% of the time I'll get a value above 93. And 2.5% of the time I'll get a value below 85. Right? Well, this tail here is almost asymptotic. It goes way out like this, right? But the probabilities get really, really tiny at the end. The probability of getting a mean like that's like 95 is like only a real small fraction of a percent, right? Very, very unlikely. Okay. Now, if I say to myself, well, I just took a sample of size 94, can I say that that's really different from my population? This group of 100 people, is that really a different population than my population A? Okay, well, if I see this, I say to myself, well, the likelihood of getting this value, right, is less than 2.5%. Okay, that's if I knew it was only going to be too high. Since this is symmetrical, I have to say to myself, well, really what I'm looking at is something that's 2.5 standard deviations away from the mean, right? Because it's 5 away from mean, the standard error is 2. And on this, I have to also account for the other side. So I know that there's less, if this is a single-sided test, we only looked at it on this side, this is less than 2.5% chance of being from this population, this sample of 100. Okay, now if I'm looking at it two-tailed, in other words, before I do the test, I don't know, and this is not most of the time, I don't know whether my new group of 100 is going to wind up being higher or lower. It could be either one. Then I have to account for the lower tail also, 2.5% at the bottom and 2.5. So I know that the likelihood of a result for 100 people being greater than 94 is less than 5%. That's the probability of that occurring if it's part of this population. Okay, if that's true, well, if it's 96, it's a very low probability. If it's 98, it's really fantastically low. I have to set a point, but I'm almost never going to get a result. That's impossible to have if I take group A. I could just wind up with all the 100 highest values in group A just randomly by, really bad luck. Okay, so in order to work practically, I have to set myself a standard. Where am I going to set the line here? What's my what level of error am I going to be willing to accept? That's called your alpha error. Okay, and in most cases, we're willing to accept an alpha error of 0.05 or 5%. We're willing to accept a chance of being wrong if we say the two groups are different of 5%. Okay, now, so in other words, if I take a look at this and I say, group A and this sample that I took are two different groups, they're not from the same group. I know that because I'm willing to accept that because it was less than 5% chance that I would get that value for a sample of 100 from this population. Okay, so so I say I'm going to reject that. I'm going to reject the idea that they're the same, and I'm going to say that those two are different. Okay, so your alpha error is 5%. So now what that means is that you have a 5% chance of being wrong if you say that they're different. You take that chance because on a practical basis, your sample size might have to be too large to reduce it even smaller, or you feel that's a sufficient level of certainty for you to work with. Okay, so now what can happen sometimes is that, gee, the other thing that can happen is that I could take a sample of 100 and I could find that the result comes out to be X bar is equal to 93. Well, if I'm going to, excuse me, 92. Okay, so 92 is around here somewhere, right? There's 92 in there. It's inside of that 95%. Okay, and I say to myself, well, gee, what percentage of the time would I get a value of 92 or higher, right? Well, I look at this and I say to myself, well, gee, I would get, that might be, I don't know, I'm going to take a wild guess and say, we get a value of 92 or higher at the area here, maybe 3%, maybe 4% of the time. And I also got to make up for it over here for the other end, and we get a value only 1.5 standard deviations across 4% of the time. Also, I'm making this number up. Okay, I add them together, and I could get this result 8% of the time. Well, in other words, if I say that this is a different population if the mean is 92 for a sample size of 100, well, I could be wrong 8% of the time. Okay, that would be my probability of being wrong. My probability of being wrong here is bigger than my alpha error, my acceptable level of error. So I say, I can't say that they're different. I just have to, I just can't draw a conclusion that this is not from this population. Well, you remember that the samples from a second population B, they're just not a single value. We could take a sample size out of this population B and we might get a value on average of 94, which would, be really different from this one, right? But occasionally we're going to get a result there of 92. We're going to get a result that we can't say is different than A, even though they are different, The probability of being, if you fail to say that they're different, right? And we'll get to this later on, the idea of failing to reject a null hypothesis. The probability of them being different, if you fail to reject that and they really are different, that's a beta error. Okay, that's called your beta error. Okay, so now what the closer these means are together for the two groups, the smaller sample size is, the more likely you are to make a beta error because you don't distinguish between the two of them. You don't have enough evidence to distinguish between the two of them. Which one of these two is worse? Well, in general, in most cases, we consider an alpha error to be worse because let's look at the outcome, the result of making either one of these kinds of errors. If I make an alpha error, I'm saying that group A is group and group B are different when they're really not. Well, let's say that I'm testing an intervention, that involves spending a lot of money, making a public health initiative that costs a ton of money and involves testing and patients and so on and so forth, even maybe involves some risk if the testing involves some risk, right? So if there's no difference between doing the intervention, A, and not doing the intervention, B, right? And I say there is a difference. Now we're going to spend a ton of money. We're going to do interventions that could be risky and so on and so forth. We could tell people to take a drug that has no effect because really there's no difference between the group that took the drug and the placebo, A and B. So an alpha error means that we're making a definitive statement that someone may act on. Okay, so that's pretty bad. Now, beta error, on the other hand, we may find that, gee, we could be wrong 8% of the time if we said that these two groups are different. Well, you may say to yourself, well, gee, I'm not going to accept that because it's got to be less than 5% chance of being wrong. Well, in that case, you might say to yourself, you know, I got a pretty good result there. I was pretty close to proving this, but not quite. So beta error, that might lead you to say, well, I'm going to take a look at the difference in these means, and maybe I'm going to go back and redo this study. And maybe this time I'm going to increase my sample size. Maybe I'm going to increase the dosage rates of the drug so that I can see if there really is a difference or not. So beta error is not quite as, the results of beta error is not quite as dramatic as the results of an alpha error. So that's why, in general, we're more cautious about not committing an alpha error than a beta